A mild steel shaft is used to connect a motor drive to a constant load torque. A foil strain gauge having a resistance of 120 ohm and a gauge factor of 2 is mounted on a shaft with its axis of the shaft as shown in the figure 1. The shear modulus of the steel is 80 megagrams. Modulus of steel is mg per meter square. The shaft radius is 15 meters and the change in strain gauge resistance due to the load is 0.24. The value of load torque is fine. So if you see, then in this question the an area of shaft surface is originally a square with sides of the unit length. Fine. So this is the assumptions what we have made. So please see carefully that the area of the shaft surface originally squares with sides of the unit length and is deformed by strain due to the parallelogram is shown. So basically we'll show a parallelogram of that. Now if you see that this the force whatever is being given, it's a shear force, so angle of shear will come into picture, which will denote by theta. Fine. So there will be a parallelogram which will come into picture because it's a shear force. So this is the parallelogram. As it is a shear which is going, so the direction of force will be this side. So you will be having a diagonal of certain length, and we are denoted it by the length of 1. So it will be 1. Fine. So now whatever the angle of shear, if we want to measure, or what angle it subtends, so same draw the line from the sides to be of 1 unit of each, that is the side which is equal the sides of this parallelogram on which the shear force is being applied. Fine. So you have this. Now just connect it with the edges of that parallelogram. Now this is the angle of shear, this theta what we have defined. So theta is the angle of shear, theta. Fine. So how we have drawn theta? We have just drawn two lines of one length, unit length, which is of the same dimension of the sides of the parallelogram, and then we have and from their endpoints we have drawn the imaginary lines towards the end of the parallelogram, and the angle subtended between the solid line of the parallelogram and the imaginary line is called as the angle of shear, or the theta. Fine. So if the angle of shear is theta, which is small, the length of the diagonal of the parallelogram is longer than the length of the diagonal of a square. Fine. So if it is a so because of it, the length of the diagonal becomes under root of 2. Fine. Because the angle of shear theta will take it where is very small, because the shear force will be very small, because of it the bending will be small, so the length of the diagonal of the parallelogram is longer than the diagonal of a square. Fine. So it is the assumption when you take a parallelogram. Fine. So parallelogram is a simple figure, okay, it's not a square basically. So if you have two opposite sides parallel to each other, so then it becomes a parallelogram. So the difference of in the length is theta by delta 2, theta by root 2. So therefore the diagonal strength we can find out by, so I'll just write it down. The difference in the length is theta by root 2. So therefore the diagonal strain is FL by L. So it is by theta by root 2 by root 2. So it becomes theta by 2. Fine. But we know that FR by R is equals to gauge factor into epsilon. Epsilon we have just found out in the above equation. So 2 into theta by 2. So it becomes equal to theta. So that is, so therefore theta is equals to FR by R is equals to 0.24. R is given 120. So you have 2 into 10 to the power minus 3 radius. Fine. So torque T. So this formula of torque T is known. So G pi R cube by 2 theta. See the formula for mild shaft in the literature. So after putting all the values, you have pi into 80 into 10 to the power 9 giga. So 10 to the power 9 into 15 into 10 to the power minus 3 to the power 3 into 2 into 10. So putting all the values and dividing it by 2, so you will be getting the value of T as 847.6 Newton meters. Fine, so this is the answer. So if you see, then option number A, 847.6 Newton meter is correct. So option number A is correct.